We already discussed in the previous episode that a DTM program M with input symbol sigma accepts an input string x belonging to sigma star if and only if it halts in the state qaccept. The language LM recognized by the program M is the set of all strings in sigma star that M accepts. For the remaining strings sigma star minus LM, the DTM may or may not halt. However, considering the formal notion of an algorithm, a DTM must halt on all input strings. Keep this concept in mind. You remember, we had considered a set of symbols sigma to encode a problem P and we call this the encoding scheme E. Then we defined sigma star, which represents the set of all possible strings generated by the symbols in the set sigma. These possible strings can be categorized into three categories, and the set of strings representing yes instances of a problem P is known as the language LP, right? Now suppose a DTM program M exists that takes input strings corresponding to yes instances and reaches and halts at qaccept, which is a final state. For the remaining strings, it also halts. We say that a DTM program M solves the problem P under encoding scheme E if it halts for all input strings over its input symbols and LM equals LP. Let us try to understand the meaning of this statement. We already discussed in the previous episode that we consider set of input symbols. Among all of possible strings, a specific set of strings x is given to the DTM program M as input. M halts at the state qaccept, and when we give the remaining strings as input, the DTM may or may not halt. We call the set of strings for which the final state is qaccept the language LM, right? Now, we use the same set of symbols to encode the problem P and call this encoding scheme E. There are three categories of possible strings, right? We say the DTM program M solves the problem P under encoding scheme E if it halts for all input strings over its input symbols and LM equals LP. It means M accepts exactly those strings that represent yes instances of problem P, no more, no less. One more point here to make. We know that problem P is a decision problem, right? Now let's define decidable problem. Decidable problems are those problems for which an algorithm or a Turing machine always halts and gives an answer either accept or reject. When we encode problem P, there were three categories of possible strings. When we give strings representing yes instances of problem P and strings representing no instances of problem P as input, the DTM halts at qaccept state for yes instances and at qreject state for no instances. Don't get confused with the third category, invalid encodings. They do not represent any instance of the problem. So, when we are discussing problem P specifically, invalid encodings are not part of the discussion. However, we already noted that the DTM halts for them as well. Since for the problem P, the DTM always halts and gives an answer accept or reject, this problem is a decidable problem. So, why are decidable problems important? To understand this, let's consider what happens when a problem is undecidable. An undecidable problem is a decision problem with yes no answers, for which no algorithm exists that can correctly determine the answer for every possible input and always halt. This means that even if we use the most powerful algorithms or advanced techniques, there will always be some inputs for which the algorithm either loops forever or produces an incorrect result. This limitation is not about time, efficiency, or hardware. It's about the fundamental limits of logic and computation. That is why we say undecidable problems are inherently intractable. They go beyond what is computationally solvable. Because we cannot solve such problems in general, we also cannot analyze their time or space complexity. Complexity theory only applies when solving is at least possible. That is why decidable problems are central to theoretical computer science. They lie within the scope of computation, and this is the reason why the P versus NP theory and broader complexity theory are developed under the assumption that the problems being studied are decidable. We already discussed time complexity and big O notation in one of the previous videos. If we define time complexity in the context of deterministic Turing machine or DTM, we can say the time used in computation is the number of steps required by a DTM program M to halt for an input string of length n. The time complexity of the program is the maximum number of steps taken over all possible input strings of length n. We can understand this better with an example. We generate all possible strings of length n. For each string, we calculate the number of steps required by a DTM program M to halt. Then, we find the maximum number of steps taken among all strings of length n. We repeat this process for all possible input lengths. The time complexity of the program is defined as this maximum number of steps for inputs of length n. Now, if there exists a constant k such that t max is less than or equal to n to the power k for all n, we say that the DTM program M is a polynomial time DTM program. Now, time has been come to formally introduce the first complexity class P. P is a class of language L if there exists a polynomial time DTM program M for which L equals Lm. The language L that we care about is exactly the set of strings that the DTM program M accepts. So the DTM program M solves the decision problem defined by L. We can also say a decision problem P under encoding scheme E belongs to class P if the language of problem PLP belongs to the class P. Or we can say a decision problem P under encoding scheme E belongs to class P if there is a polynomial time DTM program that solves P under encoding scheme E. P is the set of all decision problems or equivalently languages that can be solved efficiently. Here, efficiently means they can be decided by a deterministic Turing machine in polynomial time. Let us say a DTM exists that solves a decision problem in polynomial time. This means its time complexity grows polynomially with the size of the input string. But what can be the value of k in the expression n to the power k? Generally, values like 1, 2, 3, or 4 are observed in practice, and we can call such DTM programs efficient. Now, someone might argue, what if the value of k is 25? Would we still consider the algorithm efficient? Because n to the power 25 would be enormous even for a moderate n. The answer is that in practice, algorithms with polynomial time complexity typically have small, moderate values of k. However, if a problem currently has only exponential time algorithms and someone designs an algorithm with time complexity of order of n to the power 25, it would still be considered a major breakthrough and relatively efficient compared to the exponential time. This was all about class P. P is the set of all decision problems or equivalently languages that can be solved by a deterministic Turing machine in polynomial time. Now we are ready to start defining another complexity class. You might remember how a deterministic Turing machine works. Now imagine attaching a new component to it, a guessing module. This transforms the DTM into a non-deterministic Turing machine or NDTM. The algorithm executed by this machine can be viewed as having two distinct stages, the guessing stage and the checking stage. In the guessing stage, given a decision problem, the guessing module magically guesses a correct solution. You can think of it as a machine that all at once explores every possible path or solution simultaneously, something that's not realistic in physical machines, but useful in theoretical models. Next comes the checking stage, where the machine verifies whether the guessed solution is correct. This step is carried out by a deterministic Turing machine and must run in polynomial time. So, to summarize, the guessing stage represents the non deterministic part, and the checking stage is the deterministic part that runs in polynomial time. This entire process defines the working of a non deterministic Turing machine or NDTM, and the algorithm it runs is referred to as an NDTM program M. In one of the earlier videos, we discussed what needs to be defined to write a program or a formal specification for a deterministic Turing machine DTM, right? We specify the input symbols, tape symbols, set of states, start state, accept or reject states, and the transition function. Now, when we design a non-deterministic Turing machine or NDTM, all of these components remain exactly the same, except for the transition function. Let us look closely at what changes in the transition function. In a non-deterministic version, the transition function maps to a power set of possible actions. We write this as P of x, where x is the set of all possible moves. This means the machine can choose from multiple possible transitions at each step, and that's what makes it non-deterministic. The transition function doesn't return a single move but a set of possible moves. In contrast, in a deterministic Turing machine, the transition functions returns exactly one move for each state symbol pair. That's why we call it deterministic. The machine has only one defined path at every step. Now let's look at the language recognized by a non-deterministic Turing machine, NDTM, just as we did earlier for the DTM. An NDTM program M defined over an input alphabet sigma is set to accept an input string x belonging to sigma star if and only if the machine halts in the accept state, that is, qaccept. The language LM recognized by M is the set of all strings x belonging to sigma star for which M accepts x, that is, M halts in qaccept. For the remaining strings, the NDTM may or may not halt. However, when we talk about algorithms, especially in the context of decision problems, we require that the machine halts on all inputs, whether the answer is yes or no. This requirement ensures the machine defines a total function, which is essential to qualify as an algorithm. Now, we use a finite set of symbols sigma to encode a decision problem P, and we call this the encoding scheme E. Based on sigma, we define sigma star, the set of all possible strings that can be formed using the symbols in sigma. These strings fall into three categories, but the ones that correspond to yes instances of problem P form what we call the language of the problem, denoted LP. Suppose there exists an NDTM program M. This program halts for every string in LP and accepts, and for every string not in LP, it halts. Then we say that the NDTM program M solves the problem P under encoding scheme E if it halts for all input strings over sigma star and the language recognized by M, LM, is exactly equal to the language of the decision problem LP. This decision problem P is a decidable problem because it halts for every input string. In other words, the NDTM correctly classifies every possible input as either a yes instance or no instance and halts in both cases. If we define time complexity for an NDTM, we can say that the time used in computation is the number of steps required by an NDTM program M to halt for an input string of length n. The time complexity is the maximum number of steps taken by the NDTM for any input string of length n. In other words, it's the maximum steps among all possible strings of length n. If there exists some constant k such that this maximum number of steps is always less than or equal to n to the power k, then we say the NDTM program M runs in polynomial time. Now, time has been come to formally introduce the second complexity class NP. NP is a class of language L if there exists a polynomial time NDTM program M for which L equals LM. The language L that we care about is exactly the set of strings that the NDTM program M accepts. So, the NDTM program M solves the decision problem defined by L. We can also say a decision problem P under encoding scheme E belongs to class NP if the language of problem PLP belongs to the class NP. Or we can say a decision problem P under encoding scheme E belongs to class NP if there is a polynomial time NDTM program that solves P under encoding scheme E. NP is a set of all decision problems or equivalently languages that can be solved efficiently. Here, efficiently means they can be decided by a non-deterministic Turing machine or NDTM in polynomial time. We concluded earlier that class V consists of decision problems encoded using an encoding scheme E for which there exists a deterministic Turing machine DTM program M that solves every instance in polynomial time. However, once the concept of class P is formally established, we no longer need to specify the computational model or encoding scheme in the definition. This is because all reasonable encoding schemes are polynomial time equivalent. All realistic computational models are also polynomial time equivalent. Therefore, we can define class P more simply as class P is the collection of decision problems for which there exists a deterministic algorithm that solves every instance in polynomial time. Similarly, we can define class NP more simply as class NP is the collection of decision problems for which there exists a non-deterministic algorithm that solves every instance in polynomial time. In this video, we explored the foundational concepts of the complexity classes P and NP. With this understanding, we are now prepared to examine the relationship between these two classes, a critical step toward defining NP-complete problems. In the next episode, we will explore the relationship between P and NP. We will also introduce the concept of NP-complete problems and discuss how to prove that a problem is computationally hard. Thanks for watching. Don't forget to like, share, and subscribe so you never miss what's coming next.